The Versailles railway accident happened on Sunday, 8 May 1842, which was a day scheduled to honor Louis Philippe I. The event was planned to take place at Versailles, and among other scenes, firework and water walk were planned. About 6 o'clock, after the water walk finished, many attendants went to the Versailles left bank railroad to departure for home. The train was unusually long that day. It consisted of at least 70 carriages and 3 engines, 2 up front and 1 in the rear. Traveling at 40 kilometers per hour, one of the axles of the leading locomotive snapped it, and the vehicle derailed, scattering the content of its firebox. When the second locomotive and the carriages continued over the derailed locomotive, the carriages caught fire, trapping the passengers. In the end, the accident resulted in some significant changes to railway travel. Officers abandoned the common practice of locking passengers in railway cars. French authorities also established a commission that investigated the accident, and the committee recommended axles to be tested and replaced after traveling a certain distance. Additionally, the idea that metal could become fatigued also assisted in a solution to improve railway axles then. The phenomena of tin pest has been known for hundreds of years. Tin is one of the most common materials used in electronic products and systems. A tin pest is the formation of tin in the phase of alpha tin, which particularly happens in pure tin that transforms from white beta tin to gray alpha tin at temperature below 13 degrees Celsius. In this phase, tin is structurally weak and readily crumble powder that is not acceptable in electronic systems that must be reliable at low temperature. This transformation is accompanied by a change in density from 7.3 to 5.8 gram per cubic centimeter. The reduction in density requires the tin to expand, thus destroying the structure of original tin object. What is the fix? By adding amount of 0.5% antimony or 2% bismuth lead-free solder, tin pest can be extremely eliminated. Catalyst deactivation, the loss over time of catalytic activity and/or selectivity, is a problem of great and continuing concern in the practice of industrial catalytic processes. Cost to industry for catalyst replacement and process shutdown total billions of euros per year. What's make a catalyst as a good catalyst? Obviously, a good catalyst shows high activity. A high activity allows to use of relatively small reactors and operation at middle conditions. However, activity is not the only crucial property of a catalyst. A high selectivity for desired products is often of even great importance. Furthermore, it is important that a catalyst retain its activity and selectivity for some time. Ideally, a catalyst does not change and should have eternal life. In practice, this is not the case. Depending on the process use of catalyst, cycle life may vary from a few seconds, as in fluid catalytic cracking, or to several years, as in, for instance, ammonia synthesis. Catalyst deactivation is highly relevant for the application of catalysis, and specifically it has many challenges. As can be seen from the figure, the deactivation time varies greatly for the different processes. As just mentioned, at the lower end we found the FCC process, which has deactivation time a second. Deactivation of a hydrodesulfurization catalyst is much slower, depending on the feed, in the order of months or a year. Catalyst deactivation, also known as aging, is expressed by decreasing catalytic activity with time. Catalyst activity is the ratio of the reaction rate at a given time t to the reaction rate at the time that use of catalyst began. The course of activity of industrial catalysts with time can be described by means of several basic time. Please see the figure. Typically, the loss of activity in a well-controlled process occurs slowly. However, process upsets or purely designed hardware can bring about catastrophic failure. For example, in steam reforming of methane or naphtha, great care must be taken to avoid reactor operation at excessively high temperature or at steam to carbon ratio below a critical value. Indeed, this condition can cause formation of large quantity of carbon filament, which plug catalyst pore and volume, pulverize the catalyst pellets, and bring about the process shutdown all within a few hours. Not only does the decrease in catalytic activity lead to loss of productivity, it is also often accompanied by lowering of the selectivity. Therefore, in industrial processes, great efforts are made to avoid catalyst deactivation or to regenerate deactivated catalyst. Catalyst regeneration can be carried out batch-wise or preferably continuously while the process is running. The activity decreases with increasing operation time in manners that depend on the reaction condition and the deactivation kinetics. First attempts are made to make the deactivation slower by adjusting the operation parameter temperature pressure. The loss of activity can be gradual or very rapid. Examples are the hydrogenated treatment of naphtha with a catalyst lifetime of several years, and catalytic cracking, in which strong catalyst deactivation occurs after a few minutes. In all cases, the deactivation reaches an extent at which the conversion or other process parameters are below specification, and the catalyst must be replaced or regenerated. In practice, the original activity is not attained due to a permanent secondary deactivation. When regeneration steps are not longer economically viable, the catalyst must be completely replaced. While catalyst deactivation is unavoidable for the most processes, some of its immediate drastic consequences may be avoided, postponed, or even reversed. Thus, deactivation is sure greatly impact research, development, design, and operation of commercial processes. Prevention of catalyst degradation poses substantial challenges in the design and operation of large-scale catalytic process. There are many paths for catalyst decay. For example, a catalyst may be poisoned by any one of the dozen contaminants present in the feed. Its surface pores and voids may be followed by carbon or coke produced by cracking reaction of hydrocarbon reactants, intermediates, and or products. In the treatment of power plant flue gas, the catalyst can be dusted or eroded by and or plugged with a flue ash. Catalytic converter used to reduce emissions from gasoline or diesel engine may be poisoned or fouled by fuel or lubricant additive and or engine corrosion products. If the catalytic reaction is conducted at high temperature, Thermal degradation may occur in the form of active phase crystallite growth, collapse of the carrier pore structure, and solid-solid reaction of the active phase with the carrier or promoters. In addition, the presence of oxygen or chlorine in the feed gas can lead to formation of volatile oxide or chlorides of the active phase followed by gas phase transport from the reactor. Similarly, changes in oxidation state of the active catalytic phase can be induced by the presence of reactive gases in the feed. Thus, the mechanisms of catalyst deactivations are many. Nevertheless, they can be grouped into 6 intrinsic mechanisms of catalyst decay. First one, poisoning. Second, fouling. Third, thermal degradation. Fifth, vapor compound formation accompanied by transport. Fifth, vapor solid and solid-solid reaction. And last one, sixth, attrition accretion. As first, fourth, and fifth are chemical in nature, while second, fifth, and sixth are mechanical. The cause of deactivation are basically threefold: chemical, mechanical, and thermal. Each of these 6 basic mechanisms is defined briefly in table. Poisoning is a strong chemisorption of reactants, products, or impurities on the sites otherwise available for catalysis. Thus, poisoning has operational meaning, that is, whether a species act as a poison depends upon its absorption strength relative to the other species competing for catalytic sites. For example, oxygen can be a reactant in partial oxidation of ethylene to ethylene oxide on a silver catalyst, and a poison in hydrogenation of ethylene on nickel. In addition to physical blocking at adsorption sites, adsorbed poison may induce changes in the electronic or geometrical structure of the surface. Mechanisms by which a poison may affect catalytic activity are multifold, as illustrated by conceptual two-dimensional model of sulfur poisoning of ethylene hydrogenation of metal surface as shown in slide. To begin with, a strong adsorbed atom of sulfur physically blocks 3 or 4 top sides of the metal surface. Second, by virtue of its strong chemical bond, it electronically modifies its nearest neighbor's metal atoms and possibly its next nearest neighbor's atoms, thereby modifying their ability to adsorb or dissociate reactant molecules, in this case hydrogen and ethylene molecules. A third effect may be the structuring of the surface by strongly adsorbed poison, possibly causing dramatic changes in catalytic property, especially for reactions sensitive to surface structure. In addition, the adsorbed poison block access of adsorbed reactants to each other, and finally prevent or slow the surface diffusion of adsorbed reactants. Catalyst poison can be classified according to their chemical makeup, selectivity for active sites, and the type of reaction poisoned. The table on the slide lists 4 groups of catalyst poisoned classified according to chemical origin and their type of interaction with metal. This table lists a number of common poisons for selected catalysts in important representative reactions. Amines and ammonia are common poisons for acidic solids such as silica, alumina, and zeolite in cracking and hydrocracking reaction, while sulfur and arsenic containing compounds are typical poisons for metals in hydrogenation, dehydrogenation, and steam reforming reactions. Metal compounds like nickel, lead, vanadium, and zinc are poisons in automotive emission control, catalytic cracking, and hydrotreating. Acetylene is a poison for ethylene oxidation, while asphaltens are poisons in hydrotreatment for petroleum residual. Poisoning selectivity is illustrated in figure on this slide. A plot of activity, the reaction rate normalized to initial rate versus normalized poison concentration. Selective poisoning involves preferential adsorption of the poisons on the most active sites at low concentration. If sites are lesser active are blocked initially, the poisoning is anti-selective. If the activity loss is proportional to the concentration of adsorbed poisons, the poisoning is non-selective. As sulfur poisoning is a difficult problem in many important catalytic processes, for example, hydrogenation, methanation, Fischer-Tropsch synthesis, steam reforming, and fuel cell power production, it merits separate discussion as example of catalyst poisoning phenomena. The adsorption study indicate that H2S adsorbs strongly and dissociatively on nickel metal surface. Two important keys to reach a deeper understanding of poisoning phenomena include: first, determining surface structure of poisons adsorbed on a metal surface, and second, understanding how surface structure and hence adsorption stoichiometry change with increased coverage of the poison. Because sulfur adsorbs so strongly on metals and prevents or modifies this further adsorption of reactant molecules, its presence of catalyst surface usually affects substantial or completely loss of activity in many important reactions. Because the adsorption of sulfur components is generally rapid and irreversible, surface sulfur concentration in catalyst particles and beds are non-uniform. H2S adsorbs selectively at the enters of the packed bed and on the outer surface of catalytic particles, making the experimental study and modeling of sulfur poisoning extremely difficult. Interesting facts. There are a number of industrial processes in which one intentionally poisons the catalyst in order to improve its selectivity. For example, platinum-containing naphtha-reforming catalysts are often presulfated to minimize unwanted cracking reaction. Sulfur and phosphorus are added to nickel catalysts to improve isomerization selectivity in the fats and oils hydrogenation industry, while sulfur and copper are added to nickel catalysts in steam reforming to minimize coking. In catalytic reforming, sulfated rhenium or tin is added to platinum to enhance the dehydrogenation of paraffin to olefin, while poisoning hydrogenolysis coking reaction. Vanadium oxide is added to platinum to suppress SO2 oxidation to SO3 in diesel emissions control catalysts. Because sulfur adsorbs so strongly on metals and prevents or modifies the further adsorption of reactant molecules, its presence on the catalyst surface usually affects substantially or completely loss of activity in many important reactions. This is illustrated by the data in the figure showing the steady state methanation activity of nickel, cobalt, iron, and ruthenium relative to the fresh unpoisoned surface activity as a function of gas phase H2S concentration. This data indicate that selected metal all suffer 3-4 orders of magnitude loss in activity at 15 till 100 ppb of H2S. The surface tolerance of this metal extremely low. Moreover, the sharp drop in activity with increasing H2S concentration suggests highly selective poisoning. Fouling is the physical mechanical deposition of species from the fluid phase onto the catalyst surface, which results in activity loss due to the blockage of sites and pores. In its advanced stage, it may result in disintegration of catalyst particles and plugging of the reactor voids. Important examples include mechanical deposits of carbon and coke in porous catalyst. Carbon and coke forming process also involve chemisorption of different kinds of carbon or condensed hydrocarbon, which may act as a catalyst poisons. The definitions of carbon and coke are somewhat arbitrary and by convention related to their origin. Carbon is typically a product by CO disproportionation, while coke is produced by decomposition or condensation of hydrocarbons on a catalyst surface and typically consists of polymerized heavy hydrocarbon. Nevertheless, coke form may vary from high molecular weight hydrocarbons to primary carbons such as graphite, depending upon the conditions under which the coke was formed and aged. The chemical structures of coke or carbons formed in catalytic processes varied with reaction type, catalyst type, and reaction conditions. The catalytic reactions accompanied by carbon or coke formation can be broadly classified as either coke-sensitive or coke-insensitive, analogous to Boudoir's more general classification of structure-sensitive and structure-insensitive catalytic reaction. In coke-sensitive reaction, unreactive coke is deposited on active site leading to activity decline, while in coke-insensitive reaction, relatively reactive coke precursor formed on active site are readily removed by hydrogen or other gasifying agents. Examples of coke-sensitive reaction include catalytic cracking and hydrogenolysis. On the other hand, Fischer-Tropsch synthesis, catalytic reforming, and methanol synthesis are examples of coke-insensitive reaction. The structure and location of coke are more important than its quantity in affecting catalytic activity. Possible effects of fouling of carbon or coke on the functioning of a support metal catalyst are illustrated in figure. Carbon may chemisorb strongly as a monolayer or physically adsorb in multilayer, and in either case block access of reactants to metal surface site, totally encapsulate a metal particles and they be completely deactivate that particles, and plug micro and mesopores such that access of reactants is denied to many crystallites inside this pore. Finally, in extreme case, strong carbon filaments may build up in pores to extent that they stress and fracture the support materials, ultimately causing disintegration of catalyst pellets and plugging of reactor voids. Mechanism of carbon deposition and coke formation of metal catalysts from carbon monoxide and hydrocarbon are illustrated in the diagrams. Different kinds of carbon and coke, which varied in morphology and reactivity, are formed in these reactions. For example, CO dissociation on metals to form alpha carbon and adsorb atomic carbon Alpha carbon can react to beta carbon and polymeric carbon film. The more reactive amorphous form of carbon formed at low temperature are converted at high temperature over a period of time to less reactive graphitic forms. The rate at which deactivation occurs for a given catalyst and reactions depend greatly on reaction condition, especially temperature and reactant composition. A fundamental principle for coke insensitive reaction of metal is that the activation rate depends greatly on the difference in rate of formation and gasification of carbon coke precursors. If the rate of gasification is equal to or greater than that of formation, carbon coke is not deposited. Rate of carbon coke precursor formation and gasification both increase exponentially with temperature. Also, the difference between them varied a great deal with temperature because of difference in pre-exponential factor and activation energies. Thus, carbon coke formation is avoided in region of temperature in which precursor gasification rate exceeds deposition rate. The rate in which carbon or coke is accumulated in a given reaction under given condition can vary significantly with catalyst structure, including metal type, metal crystal size, promoters, and catalyst support. For example, supported cobalt, iron, and nickel are active above 350 degrees for filamentous carbon formation from carbon monoxide and hydrocarbons. Platinum, rhodium, ruthenium catalysts, on the other hand, while equally or more active than nickel, cobalt, or iron, in a steam reforming produce little or no carbon or coke. This is attributed to reduced mobility and solubility of carbon in the noble metals, thus retarding the nucleation processes. It is not surprising that addition of noble metal to base metals prevent carbon formation. For example, addition of platinum in nickel lower carbon deposition rate during methanation, while addition of copper to nickel substantially lowers carbon formation in steam reforming. The tips to preventing carbon deposition and coke formation include operating under conditions that minimize formation, like in Fischer-Tropsch synthesis. You have to operate a sufficiently high H2 to CO ratio so that precursor to inactive carbon formation are kept at lower coverage by gasification with hydrogen. Optimizing catalyst design, in case of zeolite, optimizing acidity to minimize coke formation. Purifying the feed to remove precursors that accelerate carbon or coke formation. For example, you have to remove of polynuclear aromatic from the feed of a hydrocracking or hydrotreating process which otherwise react readily on active sites to form coke. Where coke formation is not easily prevented, for example, in case of catalytic cracking or reforming, deactivation is relatively easy, reversed by regeneration through carefully controlled low temperature combustion of deposited carbon in air. In reaction involving hydrocarbons, coke may be formed in the gas phase and on both non-catalytic and catalytic surfaces. Nevertheless, formation of coke on oxide and sulfides is principally a result of cracking reaction involving a coke precursor, typically olefins or aromatics, catalyzing by acid site. Dehydrogenation and cyclization reaction of carbonation intermediates form on acid site lead to aromatics which react further to higher molecular weight polymeric aromatics and condense as a coke. From the mechanistic scheme on a slide, it is clear that olefins, benzene, and benzene's derivative and polynuclear aromatics are precursor to coke formation. Thermally induced deactivation of catalyst result from first loss of catalytic surface area due to crystal growth of the catalytic phase, second loss of support area due to support collapse and of catalyst surface area due to the pore collapse on crystallites of the active phase, and third chemical transformation of catalytic phase to non-catalytic phases. The first two processes are typically referred to as a sintering, the third solid reactions. Sintering processes generally take place at higher temperature and are generally accelerated by presence of water vapor. Most of the sintering and redispersion work has focused on supported metals. Three principal mechanisms of metal crystallite growth have been advanced. First one, crystallite migration. Second, atomic migration. Third, at a very high temperature, vapor transport. Crystallite migration involves the migration of entire crystallites over the support surface, followed by collisions and coalescence. Atomic migration involves detachment of metal atoms from the crystallites, migration of those atoms over the support surface, and ultimately capture by larger crystallites. Redispersion of metal particles can occur in the presence of oxygen or chloride, and the process may involve formation of volatile metal oxide or metal fluoride complexes which attach to the support and are subsequently decomposed to small crystallites upon reduction. And another way to formation of oxide particles or films that break into small crystallites during subsequent reduction. In general, sintering processes are kinetically slow at moderate reaction temperature and irreversible or difficult to reverse. Thus, sintering is more easily prevented than cured. Sintering is strongly temperature dependent. The melting point plays a central role. It is not illogical that solid-state diffusion becomes faster when the temperature is close to the melting point. The so-called Taman and Hutting temperatures indicate for the temperatures at which sintering may occur are directly related to melting temperature. Upon temperatures increases, the mobility of atom increases. First, when the Hutting temperature is reached, atoms and defects will become mobile. Later, when the Taman temperature is reached, atoms from the bulk will exhibit mobility, and at the melting temperature, the mobility will be so high that liquid phase behavior is observed. The following semi-empirical relations for the Taman and Hutting temperature are recommended to use. T Hutting is equal to 0.3 melting point temperature, and Taman temperature is equal to 0.5 melting point temperature. Actually, the temperature at which the solid becomes mobile depends on several factors such as texture, size, and morphology. For example, for gamma alumina, a highly porous material is much more sensitive to sintering than alpha alumina. For small particles, the temperature at which mobility occurs may be much lower than that indicated by the Taman and Hutting temperature. From table it can be understood why ceramic support like alumina and silica are generally used in metal catalysts. Please investigate the table on this slide. Temperature, atmosphere, metal type, metal dispersion, promoters and support, surface area, texture and porosity are the principal parameter affecting rate of sintering and redispersion. A sintering rate increases exponentially with temperature. Metal sinter relatively rapidly in oxygen and relatively slow in hydrogen. Also, depending upon the support, metal redispersion can be facilitated by exposure at high temperature to oxygen and to chlorine, followed by reduction. Water vapor also increase the sintering rate of supported metals. Specific activity based on catalytic surface area can be either increased or decreased with increasing metal crystal size during the sintering if the reaction is structurally sensitive, or it can be independent of changes of metal crystal size if the reaction is structurally insensitive. Thus, for the structurally sensitive reaction, the impact of sintering may be either magnificent or moderated while for a structure-insensitive reaction, sintering has in principle no effect on specific activity per unit surface area. In the latter case, the decrease in mass-based activity is proportional to the decrease in metal surface area. The use of in situ transmission electron microscopy technique that are capable of monitoring dynamic process in individual nanoparticles in real time can resolve the uncertainties that arise from postmortal experiments. Metal loss through direct vaporization is generally an insignificant role to catalyst deactivation. By contrast, metal loss through formation of volatile compound like metal carbonyl, oxide, sulfide, and halide can be significant over a wide range of conditions, include relatively mild conditions. Classes and examples of volatile compound are listed in table in this slide. Carbonyls are formed at relatively low temperature but high pressure of CO. Halide can be formed at relatively low temperature and low concentration of the halogens. However, the conditions under which volatile oxides are formed vary considerable with metals. Loss of nickel metal during CO chemisorption on nickel catalyst at temperature above 0 Celsius is also a serious problem in view of toxicity of nickel tetracarbonyl, the rapid loss of nickel metal, and the ill-defined adsorption stoichiometries. Researchers are avoid using CO chemisorption for measure nickel surface area, instead hydrogen chemisorption. Example of vapor-induced chemical transformation of catalyst is to inactive phase are listed in another table. Example of vapor-induced chemical transformation of catalyst to inactive phase are listed in another table on this slide. Failure of catalyst is observed in several different forms, including crushing of granular or pellet or monoliths, catalysts formed due to a load. Attrition, the size reduction and or breakage of catalyst granular or pellets to produce fine, especially in fluid and slurry bed reactors. And erosion of catalyst particles or monoliths coated at high fluid velocity. Stability too low, what to do? High conversion are often achieved when the fresh catalyst, but the conversion drop rather rapidly as the catalyst adjusts to the operation condition, and after the decay subsequently deactivation takes place continuously, also usually at much lower rate. What options do we have? What can be done to eliminate or in any case reduce the unfavorable decrease in catalytic activity? And if this is not possible, can the activity be restored and how? First, we have to understand the cause of catalyst deactivation. Second, reactor and the process design should be made in which the deactivation and its cause are taken into account. And third, good engineering practice will imply optimization of the operation conditions.